Good morning, everyone, and welcome. This is the parallel session in room 1, flood resilience in urban areas. And I think I'm very excited actually to have this early start this morning because floods pose a threat to human life, critical infrastructure, and economic operations, as we know, especially in complex, high-density urban environments. So new approaches and practice are needed to make urban areas more resilient, considering prevention, preparation, response, and recovery. And flood resilience solutions should cover the whole spectrum of these activities, from adaptation to prevention, from early warning through to urban planning. This morning, we have 6 speakers who will tackle the critical theme of flood resilience in urban areas with very interesting case studies and novel insights. So please join us for all the session this morning, and I really warmly remind you to use the Q&A chat to ask questions to the speakers. I know the interaction is a bit different compared to the usual way of conferencing, but the Q&A sessions will be at the end, and I will receive all the questions and I will propose them to the speakers, and we will have occasion to discuss all together. So please welcome with myself the first speaker, that is Miguel Balaguer, who is going to present a talk about intelligent real-time flood control and warning system in flood parks. Miguel holds a master's in hydraulic engineering and has almost 10 years of experience in water-related projects, particularly in asset management, metering systems, modeling water and sewer networks. He's currently at Hydraqua and participating in the Suez Group in projects related to urban resilience and urban emergency. Miguel, the floor is yours.
Hello, can you hear me now? Yes. Hello, everybody, and welcome. Can you hear me? Sorry.
Yes, very well.
Okay. Can you see my screen now?
Also.
Okay. Yes, I have a little problem now. Yes. Okay. Now. Okay. So I was saying that hello, everybody, and welcome to this Congress, and congratulations to the URCC Congress. My first opponents call intelligent real-time flood control and warning system in flood parks. And this is the content of the presentation. And I'm going to talk about this project was developed in Alicante. Alicante is located in the east of Spain. And this area has a weather stream sometimes. So we have an area that has a flood problems. So we need to create a solution. You can see in maps how this area was flooded many years. So we decided to have a solution, to take a solution. This is the alternatives we take into account. The first one was a retention tank. The second would be a big collector or a big collector, and the third one was a nature-based solution. We decided to construct the third one. You can see now in this image. It's a new green area. A new green area was created with indigenous vegetation and animals in the park. We have it has a social investment because citizens can enjoy it immediately as a green area. As we saw before, this is how it's work. It has a big collector that connected to the flood park. And we have many another collectors depending on the rain. we have a pump station to the treatment plant, or we can discharge directly to the sea in case the rain was too much. In this image, we can see how was the construction. This was a field near to the beach, and the different stage for the construction. It was a private-public collaboration because Aguas de Alicante, who built this flood park, belongs to the municipality called Ayuntamiento de Alicante. How how does it work? So when in the dry season, there is a maintenance level, okay, that we fill with recycled water, and when it's raining, if the raining is too much, okay, the water will be inside the park. the raining water. Does it work? So you in this image we can see two case, okay, in August 2019. It was filling up, and in March 2017. We can see the values. Okay, so the worst case for was 2 years ago, that it was empty about the 49%. Okay, and this flooding park has 45,000 meter capacity. So only we use the half of them. Okay. The question is on the topic, it's about the what about the evacuation protocol. So what happened now with the people who was hanging out in the park? So don't worry, the people was evacuated before the park was filling up. We designed an intelligent control system, an evacuation protocol. Sorry. That it has these technologies. Okay, we have a weather forecasting system, 6 water level gauge, 4 rain gauge in the area, security cameras, an electronic display, acoustic warnings, and the third system is permanently monitored and controlled 20 hours a day and all year. Okay, we can see the system control we have in Aguas de Alicante to control them with the level gauge, and the different speakers and the different technology we have it. So how it works? Well, we can see now this is the the weather forecasting system. Okay, we have 5 rain gauge in the area, and this supply information in real time. On the other hand, this is the big display we have in the entrance of the flooding park. And when we notice them, the evacuation message of the weather in case it's not raining. And we define an evacuation protocol. When it's not raining in the dry season, or we just do a weather forecasting email reporting to the municipality responsible. Okay. In the other hand, we have when the rain is 1 millimeter hour, we continue email reporting, but we saw a warning message in the display. Okay, and the police must visit the park to be prepared in case it's necessary to evacuate if the park is starting filling up. Okay, and when the rain is too much, well, we compare the different level gauge, and we know when the park is filling up. Okay, and when the park is filling up, we call to the emergency local police, municipality, etc. And we start the evacuation protocol. Okay, there is a record evacuation message in different language using the public address system and the display. And the local police will evacuate the park. And then when the park will be empty of people, the park will be closed. So the flooding park can start filling up. So the focus on this presentation was about the importance to design this kind of flooding parks, taking into account always the evacuate protocol and the monitoring system. Okay, so because this kind of park could be a perfect nature-based solution to avoid floods and pollute discharge into the sea. A new green area will be created with indigenous vegetable and animals in the park. Citizens can enjoy it immediately as a green area. And it's a reuse park because a large part of the excavation material from the ponds in the excavation was reused, minimizing the environmental impact by reusing construction waste. And the park used reclaimed water for irrigation and filling the ponds. But the question is this kind of flowing park could be very dangerous. So it should be designed to be filled very, very slowly, to take enough time to evacuate people. And the warning system and the evacuation protocol of the flooding park must be taken into account in the design phase construction to avoid risk. Okay, so this is our presentation. Thank you very much.
Thank you, Miguel. Thank you so much. I think your presentation was a great example of a practical study and actually something that even been realized. So it was very, very interesting for me to see from the project, the master plan, then arrive actually to the realization. And I'm sure everyone has really enjoyed it. Please, if you have questions for Miguel, post them in the Q&A box, and we will ask your question at the end of the session during the appropriate session. Now, I'm really looking forward to hear from Elena Cristiano, who is our next speaker. Elena is a postdoc at the University of Cagliari in the wonderful Sardinia in Italy, working in the field of urban hydrology and pluvial flood risk. Elena is going to present her work on the potential benefits of CAM green roofs on the pluvial flood mitigation in Mediterranean urban areas.
Good morning, everyone.
Yeah.
Can I share my screen?
Yeah, it's ready. The floor is yours. Thank you, Elena.
Thank you. Okay, so good morning, everyone. I'm Elena Cristiano, and today I'm going to present the work that I developed in Cagliari with my research group about the potential benefit of a CAM green roof in urban areas. As we know, climate change is leading to an increase of dry periods, but also to an increase of extreme rainfall events, which are more intense than in the past and shorter but faster. This, combined with an increase of urbanization, which we are observing in any city, is leading to an increase of pluvial flood risk. In order to deal with this problem, many blue and green solutions have been developed. For example, we have pavements or water plaza or harvesting system or green roofs. In our study, we decided to focus mainly on green roofs. Why? Because these two offer multiple benefits. In fact, it can contribute to mitigate the runoff generation, but it has also other benefits. It can contribute to the thermal insulation of the building. It can decrease the temperature of the environment, contributing to decreasing urban heat island. It attracts many species of insects, and depending on the type of vegetation that is installed on it, so it increases the biodiversity that we can have in the city. And moreover, it adds an aesthetic value to the city, which is nice, and many studies have shown that it can help the well-being, the human well-being, increasing concentration and improving the quality of life of people. And another reason why we choose to focus mainly on green roof is that because in Cagliari, we have, at the University of Cagliari, we have a special green roof located at the entrance of the engineering faculty. As you can see from this picture, this is the entrance of our faculty, and above it we have a green roof, which is a really particular green roof because it was there since the 80s, and it has spontaneous vegetation. So probably in the 80s, when it was constructed, there was another type of vegetation which died because of the hot summers and because of the really low, actually absent maintenance. And on top of it, some natural vegetation growth. And what we know for sure is that no one took care of this vegetation since now, when we decide to install some instrument to measure the retention capacity of this tool. So as we can observe, this tool is made of two hydraulic independent modules. So you can see the red one, and that is draining on the left side, and the green one, which is draining on the right side. And we decide to measure the retention capacity of these two independent modules. The vegetation, no, sorry. So as said, the two tanks are draining on the two sides, and we located some tools, some rain gauge to measure the outflow from these tanks. Moreover, there are some rain gauges located really close to the faculty, so we can have a measure of the rainfall and of the corresponding outflow from the green roof. About the vegetation, as I was saying, this is a typical vegetation from the Mediterranean area. Is an Americana, which is characterized by acrosolaire acid metabolism, which means that this type of vegetation has a low evapotranspiration rate with a daily stomatal closure. And as I said, it has actually no maintenance cost. It doesn't require any artificial irrigation. And it's capable to survive with during very extreme hot summers. We represented with a conceptual model the hydrological behavior of the green roof. Here you can see a schematic representation of the model, which was developed by Professor Viola, and that we adapted to our study case. We calibrated the model, and during an observation time of 1 year, during 2019. And what we observed was that the model was actually quite good, quite capable to estimate the peak of the outflow and the timing. So both in terms of timing and in terms of intensity, the model can really well represent the behavior of our green roof, both right and left side. We identified 6 rainfall events during this year. Here you can see the rainfall events on the top, and we investigate what was happening in terms of outflow. We investigate that with the help of the index of retention. The index of the retention that you see here expressed by the formula, it's an index that represents the percentage of rainfall that is actually retained by our green roof. It can vary between 1 in case of there is no outflow, so the entire rainfall event is retained in the green roof, and 0, where is the situation where actually the soil is saturated, so the rainfall is directly going out from the green roof. We investigated the index of retention for the 6 rainfall events that I mentioned before, and we tried to relate this index of retention with some event characteristics. In particular, we focus on the antecedent dry period, so we investigate how many days before the rainfall events were dry, so there was no rainfall, the duration of the rainfall event, and the intensity of the rainfall event. Actually, we noticed that there is a quite interesting relation between the index of retention and the duration of the event itself, as we were expecting. In fact, that long rainfall events led to smaller index of retention. Once we calibrated our model, we decided to investigate, we decided to compare a green roof with a camp vegetation with a potential, an hypothetical green roof with a seed-tree vegetation, so with a more common vegetation that is usually installed on green roof. And so with the calibrated model, we represent a really long time historical series from 1947 to 1997. And we compare the green roof with these two types of vegetation. There is one small note that seed-tree vegetation applied in Mediterranean areas requires some irrigation. So if we would install on a green roof a seed-tree vegetation, which is generally grass or small plants, they need irrigation during summer to survive. So during our simulation, we hypothesized some irrigation for the seed-tree vegetation, while for the CAM vegetation, we decided to not apply any type of irrigation. This is the long time series simulation, and as you can see, of course, the outflow from the CAM vegetation is higher, but it's actually quite similar to the seed-tree vegetation. We investigated the index of retention for these two conditions, limiting it to intense rainfall events and extreme rainfall events. So the 75, we investigate all the events above the 75 quantile rainfall and all the events above the 95 quantile rainfall in order to represent these two conditions, intense rainfall events and extreme rainfall events. And what we observe, yes, I'm running out of time. What we observe is that indeed for both this condition, both green roofs perform really well. Of course, seed-tree vegetation is better, but it's actually slightly better. So we would expect the camp vegetation to perform worse. To conclude, as I said, we observed that both green roofs have a good capacity, good retention capacity. And what is important is to notice here is that seed-tree vegetation, which is usually not considered for green roof, in Mediterranean areas can perform really well. And with the fact that it has no maintenance cost and it doesn't need additional irrigation, is actually to be considered for the installation of green roofs. Of course, this is a synthetic study, so there is the need to investigate other types of vegetation. And it could be interesting to investigate some multi-layer green roof which combine the green roof structure with the rainwater harvesting system. And with that, I would like to thank you for the attention. And yeah, I'm waiting for the question session later on.
Thank you, Elena. Great presentation. Thank you so much. It was great to see, again, another real example of a green roof, which I actually am quite fond of green roofs because I think it could be really a solution for our city, while in the same time bringing co-benefits such as the increase of diversity and given some spaces in cities where we don't have many green areas. So I think it's very relevant to conduct research in this field. I remind again to pose all your questions to Elena in the Q&A box so that we can ask her in the appropriate session. Please don't be shy and ask everything you have in your mind. Now it's time to go on, and please welcome with me Christopher Davies, who is going to present about strengthening urban resilience to flooding in Yangon using sustainable urban drainage system. And Christopher is a chartered civil engineer and principal consultant within the water and sanitation team at IMC Worldwide. He currently works on a range of international development projects across Asia and Africa. His past experience includes also humanitarian response and the private engineering sector. So, Christopher, if you are ready, I will leave you the floor and time for your presentation.
Thank you very much. Good morning, everyone. Thank you for the introduction, Maria. I'm going to talk about our recent experiences of using SUDS to strengthen urban resilience to flooding in Yangon in Myanmar. I will first give an overview of the project, team, and flooding in Yangon. I will then introduce our 3 case studies where we explored using SUDS to alleviate flooding. Finally, I will review our recommendations and touch on our project limitations. So our team consisted of 14 national and international experts working closely with a dedicated technical working group within the local authority, as well as working closely with key representatives from the local townships. A bit about Yangon. So with a population of just over 5 million, Yangon was the capital of Myanmar until 2006. Yangon is flat and subject to a range of flooding sources, both natural and operational. There is a monsoon climate with extremely high rainfall intensities, and Yangon is also susceptible to storm surges associated with cyclones. The result of this, well, recent economic assessments estimate the annual cost of flooding to be $1.7 billion per year. As with many cities in the Southeast Asia region, Yangon has experienced rapid urbanization in the past 20 years. To bring some focus to the project, our team looked into 3 case study areas, namely formal developments, this is commercial and residential, industrial zones, these are typically factories and warehouses, and informal development, so that's low-cost residential and informal market areas. Within these case study areas, we talked with a range of stakeholders from public, developers and local authorities to understand perceptions of flooding hotspots and the causes of flooding. To complement this information from the interviews, we also built hydraulic models using EPA's stormwater management model. This used data from some existing models of Yangon drainage, as well as a series of field surveys from our team. We were able to target key flooding issues in our case study areas and present these to the authorities. So a common issue, by no means common to Yangon, by no means just in Yangon, there was an increase in impermeable area resulting in larger runoff volumes and peak discharge rates. Additionally, and this is a major problem you can see here, developments often significantly raised levels within their site, displacing flooding to other nearby townships, typically often also the poorer areas as well. This can be seen in our formal development case study on the right there. So the above picture was the before. We used satellite photos and old surveys to show that this used to be an area that flooded regularly. And then once the development was built, they built this up about 2 or 3 meters, and we were able to show that the flooding was displaced to Ward 2 north of the site, which was also corresponding with reports from local residents. There are also flooding issues due to blockages in the network, particularly due to solid waste, but also because of encroachment over key drainage assets. So why would SUDS help alleviate flooding? Well, essentially, we're trying to reduce load on a public system that is already very overloaded. We developed our case study models to consider the principles of source control and flow restriction, again, using imagery to demonstrate these measures. For instance, here, you can see that this is the same formal development I showed before, but obviously a different view. And we were trying to show a consideration for SUDS and maintaining the flood storage on site. It was important for us to clearly demonstrate how this approach may limit development in its traditional sense as well. We brought these findings together in a series of policy notes, including technical SUDS guidance for developers and policies on the planning process, working closely with local authorities. These policies were then applied in case study areas to demonstrate effectiveness and understand viability. Ultimately, we're trying to create an enabling environment where landowners and developers have an incentive to adopt SUDS as a core part of the development. This is the images here are industrial zone case study, where we were showing flooding in its current state, possible SUDS solutions, and then modeling again for how this would affect the site if everyone in the industrial zone adopted this approach. We also developed flood zone maps across Yangon to help authorities target critical development. Many of you will be familiar with flood zone maps, but it was all quite new to the authorities in Yangon. We created these by overlaying a series of flood hazard maps, looking at flooding from pluvial, fluvial, as well as restrictions to the tidal flooding. We were operating with limited data, and this is one part I'd be interested to discuss further with anyone with experience in this creation of flood hazard maps. So how effective can SUDS really be in Yangon? Well, we could only really demonstrate a practical level of source control up to a 1 in 10 year rainfall intensity. After that, we were predominantly looking at policies to manage exceedance flow. I've mentioned the challenges with the lack of data. This is particularly concerning given that we know climate change will intensify storms and the associated surges. Something a lady from the University of Philippines spoke very passionately about yesterday, and it's an issue for the whole region. We also have challenges convincing developers and authorities of the benefits of SUDS, particularly when existing regulations on urban flooding are weak. In the formal development, we showed this could mean entire blocks have to be omitted from the development. So as an overview, I've talked about the range of flooding sources affecting Yangon and our case study approach, how we use this to assess specific issues and solutions. I've also touched on our policy recommendations for mapping and technical guidance, and also the planning process. I would like to emphasize at this point that I only see SUDS as part of the solution, largely due to the high storm intensities, also susceptibility to flooding from tidal surges. There are lots of heavy infrastructure projects under preparation in Yangon, and I'm very supportive of these. So next steps for us are to continue to develop policies with the authorities, and also look at a new project to identify and improve key drainage assets. Thank you for your time.
Thank you, Chris. Thank you very much. It was great to see a project in a different part of the world and in a challenging country such as Myanmar in terms of data availability and everything that relates to this. So it was very interesting, and I thank you for your presentation. Now I'm very happy to introduce Professor Manuel Gómez, who is a full professor in hydraulic engineering at the University Politécnica de Catalunya in the Flamen department, which is the Institute of River Dynamics and Hydrological Engineering. Professor Gómez is going to talk about the relevance of surface drainage systems in the flood resilience of his city. Please, Manuel, when you're ready, if you can share your screen and take the mic, the floor is yours.
Okay, thank you very much, Maria. So I'm going to talk about something slightly different as of the presentation this session. It's just about those small elements that we have usually placed on the surface of the street that are the who are responsible of the flow transfer between the surface and the sewer. As in this case, we're going to talk about the transfer between the sewer to the surface and to produce more floods in this area. Just a minute. So what happens when you run floods? These are two pictures, some of them just even in Barcelona, that when the sewer system gets pressurized, there is a flow transfer between the sewer to the surface of the city. So it's the street network that belongs to the drainage system receives an extra flow that can suppose some serious problems sometimes. So usually the inlets have been studied just in the sense of the water flowing from the street to the sewer, but a few studies, or almost no one, have focused in the inverse process, so the transfer of flow between the sewer and the street. What are the main problems that we can do in the operation? So as I said, most of times the previous study has focused on how much water can be introduced to one single inlet. But there are several problems in some cases. For instance, we have observed in our cities local floods due to the lack of enough inlets in the district, and sometimes even to the poor performance due to the clogging. Many times you see here in some pictures that the inlet could be completely covered by leaves or by papers and so on. If we combine all these effects, we can face serious problems for vehicles. No problems if we can acquire some monster truck like this one. Problems for bikers, or even problem for pedestrians if you're not used like these ladies in Brazil. The traditional studies, as I said before, were basically how's the flow between the surface to the sewer. This is a picture of the platform we have in laboratory in the Technical University of Catalonia, the School of Civil Engineering, where we have tested the most usual inlets in the city of Barcelona. And we have arrived to describe the efficiency of the inlet as a characteristics of the flow along the street, this ratio between the flow over the water level, and this potential low can be used to characterize the hydraulics in the sense from the street to the sewer. But especially in the last years, the drainage analysis in many cities has been done using this approach of the dual drainage consideration. So a joint analysis of what happens on the sewer and what happens with the surface flow in the urban areas. Usually they use a 1D modeling for the sewer system, and most of times with a 2D approach for the street flow. So the connection between these two levels is basically done through these inlets, the manholes, and so on. So the flow transfer in both senses, street to sewer, sewer to street. The transfer process, as I said, can be seen here. So at the beginning on the left is when the the sewer system is not fully pressurized. maybe the flow goes from the street to the sewer. But as far as the flow on the sewer increases, we can arrive to the situation, for instance, on the right, where some flow exits from the sewer and arrives to the surface level, increasing, producing more problems on the local floods. So the specific objective in this research was to, can we express the hydraulics of the exit flow from the sewer with a typical expression as an orifice, for instance, and just to, can we describe the discharge coefficient for these grades in case of pressure flows? Unfortunately, this is a few reference of work on this, especially field tests or laboratory tests. And for instance, in several commercial codes, those discharge coefficients were suggested about the typical value of 0.6. This is a reference, for instance, for an emptying tank. It would be possible also to analyze the energy loss coefficient, but that's another history, and this is a question in this presentation. So we modified our experimental setup. The idea is how to produce outflows from the sewer network to the surface, in this case to our platform. Here, just you see in the upper part this expression, in this picture, the inlet and how the flow goes through this pipe, producing the outlet, the outflow from this. Again, this is the type of the first of the grade we tested. And we measured the water elevation over the grade by hand using a limnimeter. So we decided to use around more than 20 points measure. So for the estimation of this discharge coefficient, what do we have? The outflow is imposed by yourselves on the lab. The CD is what we're looking for, the discharge coefficient, including all the characteristics of the energy losses, the shape of the grade, and so on. So the G, the gravity acceleration. The AH is the area of holes of the grade, that's something not provided by the manufacturer. And this delta H could be, it could be the water level above the grade. For sure, the water level is not constant all over the grade, so that's why I decided to measure in around 20 points just to get an average. These are some pictures of how it evolves when the outflow is just 10 liters per second, it's very small over elevation. But for 30, 40, and 50 liters per second, we see that the over elevation above the grade could be more important, more relevant. I have a nice video, but it was too heavy, so I eliminated from the presentation. Okay. As I said, this during the operation, during the outflow, we had to measure the grade, the water elevation over the grade. So we could measure at 20 different points for each test case, in such a way to consider, let's say, an average value of the over water level above the grade. We can see that it's not constant, moreover it's oscillating, so the measurement process was a nightmare, but it was finally done and accomplished and so on. So what do we get? And that's interesting for the results here. So what about the discharge coefficients? What we saw is that for the flow tested between 10 to 50 liters per second of the outflow from the sewer, the discharge coefficient obtained varies between 0.15 and something less than 0.4. So it's not close to 0.6 suggested by most of the commercial codes. Moreover, what we saw is that the discharge coefficient increases with the outflow. It's not a constant. The value could multiply by 2 and sometimes close to by 3. What is the influence, for instance, with the longitudinal slope? But we saw that this longitudinal slope has almost no influence. We can consider that once the flow value is the dominant reference for the hydraulics of this process. So slight variation, but we had no problem to accept that for different longitudinal slopes for one flow, the discharge coefficient could be completely constant with no difference. All the tests were made with the same value of transverse slope. It's a 2%, that is the usual value recommended in most local guidelines all over the world. In parallel with this laboratory test, we did some numerical analysis with a 3D computer code. We used a commercial software called Flow 3D. It's a licensed software, it's not a public domain one. including the Reynolds average Navier-Stokes equations with the chi-epsilon model, the renormalized and normal group, and with a volume of flow model just to define the free surface in this in the analysis. So we compare the water levels that we found in the lab with the water levels we got from the numerical analysis, and were quite similar, surprisingly. Yes, I say that surprisingly because when you try to compare many times the observed in the lab or in the field with the numerical analysis, sometimes there are some distortions. But in this case, I can tell you, and you will see later, that we compared the discharge coefficients found from in the laboratory text and the numerical test, and you see here that the values were quite similar. Just the numerical procedure overestimates very slightly the discharge coefficient, but what is interesting is in all cases, those values are below the suggested value by some codes of practice. And just to finish, so let's say that the flow transfer in between the streets and the sewer, and in both sense, especially for the dual drainage concept, they're a key element in the analysis of the surface flow at the streets. As I said, the usual application of some discharge coefficient must be verified properly, because unfortunately there was few or no reference about the no, usual values. As I said, the typical value suggested in many commercial software is far from the observed values we found in the lab, and other authors found similar values in some other studies. One side conclusion is that the process can be done better in the labs, for sure, will be the most interesting procedure. But anyway, even with a 3D numerical computer code, results could be similar. So this could be another approach for practitioners or people who want to know which one are the CDs, the discharge coefficient of their own inlets. So as I said, the purpose of this results is that the discharge coefficient can be used to improve the dual drainage modeling approach in urban flows, allowing to describe much better and in a more realistic way the flow transfers in between the sewer and the surface flow. In this case, was the pressurized flows in the street. And I think that's it. I try to adapt to the maximum time. So thank you for your patience, and thanks for the presentation, and to the organizers. Okay.
Thank you, Manuel. Great, another great presentation. Actually, I would like to thank you, all the speakers so far, so keeping the time so well. I'm really impressed, and it's fantastic. So we will have time at the end for the question and answer session. So again, I remind everyone to write your question through the chat for this presentation and all the presentation before, because there will have time for discussion at the end. Thank you, Manuel. A great presentation about actually something with laboratory testing that is always super fascinating for me, especially when you have a good comparison with the reality. So well done. And I think now it's time to move on to the next presenter, Alejandro Ortiz, who is a director of projects at BCASA at Barcelona City Council. And Alejandro is going to present about the Barcelona Sewerage Master Plan, especially looking at the Urban Drainage Master Plan. So Alejandro, if you can share your screen and turn on your camera, it's time for your presentation. Thank you.
Okay, thank you.
We can't see you. I don't know if your camera is off by chance.
It's off? No, it's on? No?
Thank
Okay.
you. Perfect. Yeah.
I want to share. I want to share, but I can no. Okay.
Yeah, perfect.
Do you hear me? Okay, and do you see the? No.
Yeah, we
It's
don't
okay?
see you actually. but the presentation is working well.
Okay, thank you.
But
Thank you.
is your camera off by chance?
My camera it's off.
We can't see you.
Ah, yes, you can see me. You can see me.
No, we
And
can't
hear
see
me?
you. No, you should turn your camera on if possible.
Ah, okay.
Okay, perfect. Now the setting is spot on. Thank you.
Okay.
Yeah,
Okay.
you're good to go. Thanks.
Okay, it's okay. No, it's working. Okay.
Yeah, perfect. Thank you.
Perfect. First figure shows different milestones in the different Barcelona drainage plans. Barcelona has seen 7 master plans that have aimed to strengthen and improve the city sewage system by implementing innovations and providing solutions to various challenges. Barcelona's main resilient goals include in the new master plan as called as PEDISVA. The master plan for sewage system in Barcelona, PEDISVA, is an urban planning instrument designed with economic efficiency criteria in mind to reduce the risk deriving from the flood hazard and overflows, while protecting people, property, and the environment, and considering the effects of climate change, first adaptation to climate change threats, ecological and environment protection, and planning sustainable maintenance. The effects of climate change on rainfall extreme and moderate events in Barcelona. Figures shows a comparison between the design rainfall for a 10-year return period calculated with rainfall data up to 2018 and the forecast for the period 2071-2021. According to the climate change coefficients considered in the RESCCUE 8.5 scenario. In blue, you can see the current rain, and in red, the future forecast. This variation in the rainfall model means an increase of 17% in the intensity of rainfall in Barcelona with a 10-year return period. And climate change impact on 10 years return period flood hazard, considering the climate change with a hydraulic model construction. Diagnosis of the flood risk resulting from the Barcelona current rainfall model indicates that drainage system saturation would expose 24% of the city to a high risk for pedestrians and road traffic. However, if we take the climate change scenarios into account, the diagnosis predicts a further 4% increase, up to 28% of the city exposed to a high risk for pedestrian and road traffic safety. Even so, wastewater overflows into resilient environment, it's responsible up to 30% of beach season time year with high risk for people health. The flood risk management and environment measures over the coming 80 years included in the PEDISVA, in order to comply with the environmental and drainage management criteria, the PEDISVA puts forward a set of strategies that entail a change in the traditional drainage model, combining developing new sustainable urban drainage system, as called SUTs, and expanding and improving sewerage and drainage system infrastructure. The total cost of the planned measure rises to 1,400 millions. First, urban sustainable drainage system measures included in the master plan. Drainage elements on the street, the PDISFAT envisage Barcelona being equipped with a total surface area of 180 hectares strategically spread around the city. Second, a set of 10 rotation points in Coselola natural area. And third, a development plan for green roofs in building. The integrated combination of the suites can manage 28% of the total 1 year overflow, equivalent to a 5 cubic hectometer, and reduce the risk to mobility by 34% at 10-year return period, and reduce the risk by 14% at 500-year return period. And structural measures included in the master plans, anti-flooding tanks, PDISFAT envisage Barcelona being equipped with 38 new units with a total volume of 1 cubic hectometers. Now, existing 12 units with a total volume half cubic hectometers. Anti-combined sewerage overflow tanks. PDISFAT envisage Barcelona being equipped with 15 new units with a total volume of half cubic hectometer. And primary and local network expanding. PDISFAT envisages Barcelona being equipped with a total 238 kilometers of a new network, now existing 1,600 kilometers. And maintenance sustainable. PDISFAT envisages moving towards a renovation rate of 1%, repairing 16 kilometers a year. And overall assessment of tangible impacts in different scenarios, business as usual, and future applying the PDISFAT investment. Expected annual tangible damage, EAD, due to the sewage overflow and drainage system, taking the effects of the climate change into account, is 100 million. The future scenario applying the PDISFAT investment, the EAD can reduce up to 80% from 100 to 20 million. And the cost analysis, cost benefit analysis, CBA, shows that PDISFAT is an efficient master plan comparing cost and avoided damage. The figure shows the result of the CBA applying the PDISFAT investment. In the actual scenario, business as usual, the EAD is 100 million. After applying the master plan measures, the EAD is reduced to 22 million, having a cost of 28 million and a net benefit of 55 million in annual equivalent present value. Then, main challenges. This is the first plan to consider climate change forecast in each precipitation model. This is the first plan to include hydrological, flooding, and maritime models. This is the first plan to include measures to adapt to and mitigate climate change. And this is the first plan to involve such solution as alternative to traditional solutions. And this is a basic tool for urban resilience and risk management. Last, this is the first plan to include economic efficiency criteria and a cost-benefit analysis. And that's all. Thank you for your attention.
Thank you, Alejandro. Thank you so much for your presentation regarding the Barcelona Master Plan for Urban Drainage System. It was really interesting, especially looking at the benefits that you can get by implementing such measure. I mean, up to the reduction of damage of 80%. I mean, this is a really impressive. Thank you so much. And now, last but not least, I'm very happy to introduce Jackson Téllez. And Jackson is a technician at the Consorci Bezos Tordera, and he holds a PhD in civil engineering of the Technical University of Catalonia. He's also doing research in the Flamen department at the University of Catalonia, Barcelona. And today he's going to present about monitoring combined sewer overflows in Consorci Bezos Tordera under the Spanish Royal Legislative Decree 2012 framework. Please, Jackson, if you can share your screen and show you up, it's time to have the floor for you. Perfect. Also unmute yourself and you will be good to go. Jackson, you have still to unmute yourself, clicking on the mic that should be on the bottom. Thank you. Perfect.
Perfect. Now, good morning. Thank you for the presentation. Sorry. Okay, I will start my presentation. This work was collaboration with the Flumen Research Institute of Technical University of Catalonia and was elaborated in Consorci Bezos Tordera. This presentation is divided in 3 parts. First, I will do some introduction about the Spanish regulation 1219 of 2012 and the accomplished in the ambit of the Consorci Bezos Tordera. The second, I will speak about the study of the sensor placement for combined sewer system monitoring in the Bezos River Basin. And the third part, I will speak about the study of sewer modeling of sewage network in the ambit of Consorci Bezos Tordera 2. It's important to know the pollution of receiving water bodies resulting from combined sewer system, especially in rain events, is a common problem to tackle in the cities, sanitation facilities, management, which have a dramatic impact in the environmental. Before 2012, traditional overflow has not been given too much importance, but after the Spanish regulation, established a quantification of the spill volume and water quality during these events, as well as their periodicity, is of paramount importance. Now, we need to focus in the elements of outlets. Now, overflow, now the element of interest, but we need to know the characteristics and the geometry, topography, and the boundary condition, because this is important to know the real behavior of the overflow and of the outlets. In the past, in Spain, the elements of interest were manholes, pipe, pumps, and treatment plants, and they forget to study. They didn't consider the outlet as important elements. After the Spanish regulation, they established that the company and public institution involved in urban water drainage service are compelled to monitor, detect, and quantify direct discharge into the environment. This standard established that the company and public institution, they need to monitor to quantify the discharge. Okay. Also, it's important that this standard is in Spain is to minimize the overflows in order to control the effects on people, animals, and environmentals. For this reason, in the last year, in Consorcio Bezos Tordera, installing new sensor for monitoring the overflows and also start to do some numerical simulation in some network, the ambit of the consortium. Here, I will explain some deadlines established by the Royal Decree 1219. Now they propose some schedule. The first task is inventory of overflows for industrial and urban areas more than 2,000 equivalent inhabitants. The deadline to present the inventory were the end of 2014, and for equivalent inhabitants more than 50,000, the end of 2015. After that, they need to quantify the overflow system and start to do the annual report of overflows from 2016. And in the end of last year, 2019, they need to give the inventory of overflow point of retention solids. This is the schedule. But also it's important that this standard established that the discharge flows and water quality must be quantified. And now we know the regulation of the Spanish regulation. Now in the consortium, we need to accomplish the Royal Decree 1219 of 2012, and we need to report to the Agencia Catalana del Agua. In order to accomplish this regulation in the consortium, they install a lot of instruments in some overflow, some outlets point for the control of discharge in the period of rain. We make this, we find some difficult things in this stage because sometimes we have the outlets, we have different topography, different geometry, and it's difficult to install sensors. Also, it's impossible to install sensors in all the outlet points because we have a very big basin. Also, we need to have a lot of human resource in order to install sensor, also to maintain the same. Another importance for this reason, in the consortium develop like a project in order to find the methodology to perform sensor placement choosing the optimum set of the outlets to monitor. This will be an advantage to choose the outlet point to install sensor. And the methodology that now in the consortium, we have around 70 sensors installed in Besos River Basin. In the left, the figure of the left, we can visualize the map of GIS with the location of outlets. Here we have, for example, a map with the system Granollers, Lagosta, and Montornès. With this study, we can say that we can take the best location of sensor placement of 3 different systems as Granollers, Lagosta, and Montornès. We evaluate the new location or point of outlet necessary to install sensor. After that, if we have these positions, the second stage was to sensor installation. Here we can see the sensors, and also we have the data logger. The data logger, normally we use a box in order to avoid the damage of the data logger. And also because we have a big system, we need to connect all the sensors through the SIM card and Wi-Fi network to a SCADA of the monitoring plan, because the technique needs to visualize if we have some overflows in the network. We can see some sensors. And in conclusion, identify the best location of the sensor placement is advantage for us because we have a lot of outlets and it's impossible to install sensor on each outlet. Selection of the best outlet set to monitor wastewater network. And the third part of the presentation is numerical modeling. In this case, we choose the Agua Freda, the simulation of Agua Freda was carried out in Congos. We install a flow meter in order to calibrate the model. And also the rainfall data was also obtained from Agua Freda meteorological station controlled by MeteoGIS. The simulation has been carried out in the SWIM 5 program. We obtained 5 different events. the rain stage date in 2018. We use the first for calibration and the other for validation. This is some result of the simulation. You can see some pipe and the network developed in SWIM. Also, the first result, hydrograph shifts. We can see here the blue is the rain, the green is the flow meters, and the red is the simulation. We can have some offset and we have some shifts. After the calibration, we correct these events, San Pancracio, and we can see better result of the simulation. After that, this is accuracy of the model of Tani Agua Freda, San Pancracio for calibration. We have the peak flow and the total flow. Only we can see that we have a good result of simulation. We can say only San Areneo event present low precision of the model. And it's important to note that for calibration, we need the measured rainfall and flow rate required to perform the model calibration. And we can see that we have a good calibration of the model, and we need to have more results in order to validate better the model. Thank you for the attention. That's it.
Thank you, Jackson. It was great to end the presentation with yours, which is another applied case study, and it was really interesting to see your input into that. I think now we have time to open the floor to questions, and I have already questions coming up, and I think we can start from the beginning. So the first question would be for Miguel. And Miguel, this question is from Eduardo Martinez Gomariz, and he's asking about what's the residents' perception of this impressive infrastructure? Because he guesses that during the project stage, there was more citizens' complaints than nowadays. Then they can see how effective this is. So I think it was like he's wondering about, the perception of the residents before the realization of the structure. Miguel?
Now, can you hear me now?
Yeah.
Maria? Yeah. Yes. So I think I live very near to this flooding park. So I think before the construction of this flooding park, there was just a field with no use. So I think the people have no complaint about it, because now it's a very green area. You can just hanging out and walking around with your children and to see the birds, and it's very, very, very beautiful. So the most of days is used for citizens, because usually it doesn't rain here in this area in the Mediterranean. So I didn't listen any complaint about it.
Thank you. And the second question is for Elena. And the question is from Eduardo Martinez Gomariz. And he liked to set up an experiment. I mean, supposing the hypothesis that it is possible to set up a new experiment of a green roof in another city, like, for example, Barcelona. What's the way to select appropriately the vegetation to test in a different context as opposed to Cagliari? Can you give suggestion about that?
Okay, so well, I think the climate in Barcelona is quite similar to Cagliari, so a camp could be a good experiment, so a good way to test it. The climate is similar, so I think Barcelona can benefit from it. It really depends on the type of climate that you have. So, of course, if you have, let's say, a bit more rainy and maybe less hot summer, the other vegetation has to be preferred, like C3 vegetation has to be preferred. But I think in Barcelona, it could be a nice try also with some camp vegetation.
Thank you, Elena. And let me see about the question. Yes, next question is for Chris. And the question is from Saktirat Kevurner. And he is thanking you for the presentation, of course. And he's asking, how do you embrace the sustainability in the urban drainage risk mitigation? Since one size does not fit all, what would be your opinion in redesigning the costly urban drainage capacity?
Yeah, that was something that struck me from the Barcelona presentations as well, that actually there was a lot of focus on looking at the wider kind of infrastructure. Our approach is is working with developers, I guess a kind of smaller scale, but then something that was very replicable, and trying to set out policy guidelines. There's really nothing there at the moment, but that is the challenge, which is how do you make one policy which affects lots of different developments. So that's why we're trying to consider the principles of source control and flow restriction. And then actually within each site, the solution to that will be different. It will be a green roof, it will be a basin, it might be underground storage. And we're trying to encourage innovation, but the best innovation comes from designers. And a risk of insulting others in the group, it's the authorities that set the guidance and the designers that implement it. So yeah, I think that's how we can make one solution which is adaptable across a very variable city.
Yeah, makes sense. Thank you. Next question is for Professor Manuel Gómez, and the question is from Beniamino Russo. He's saying that during these days, several experiences about 1D, 2D, dual drainage models have been presented. And he's asking, which is your opinion about the possibilities and barriers for potential formula or discharge coefficients implementation in 2D overland flow models?
Okay, thank you for the question. So we presented our formulation was originated at UPC years ago of this potential formula, potential law, but we realized that for some practitioners it was difficult to apply it. So people is more used to use commercial computer codes, and in most of them, if not at all of them, this discharge coefficient formulation is included. So that's why we decided to initiate this in terms of discharge coefficient information for the practitioners who want to use the computer code. So no matter is 1D or 2D, so the idea in the surrounding area of the inlet, usually the simplest form is a 1D analysis. So the flow transfer between the sewer to the surface can be easily modeled with this expression with no difficulties, and it's much simpler. And in all the commercial codes, like Urban, InfoWorks, Win5, and so others, this orifice description is presented. The problem was basically related to which discharge coefficient to put it. And that was the problem, that depending on the value used in the analysis, the results could overestimate or underestimate the surface flow, and that could change completely the results in some areas. Yeah.
Thank you, Manuel, very much. And the next question for Alejandro, and the question is from Grant Vanson, and he's asking which stakeholders were involved in the creation of the Barcelona Drainage Master Plan and who were the key decision makers?
Okay. Stakeholders, the first is stakeholder is the CASA, is a company, a public company, Barcelona Ciclo del Agua. Another stakeholder was Aquatec.
And how was the process to involve them?
What?
Like the process to involve them.
the process it's through a contratation, external contratation for methodology of the CBA, the cost-benefit analysis.
Thank you. Thank you very much. The next question is for Jackson, and the question is about sensors, and the question is about what kind of issues did you have associated with the sensors? Any difficulties in applying them or retrieving the data, cleaning the data?
Hello, hi.
Hi.
Yes, we find some difficulties, especially the coverage of internet, for example, or the problem with the coverage of the SIM card and coverage with internet, because all the sensor, the data logger need to connect to the treatment plant or to the SCADA. And sometimes in some point of the city, it's not possible to have coverage of internet. Sometimes impossible to communicate. And another problem that we have is because we have different kind of outlets, and sometimes it's not possible to install a sensors, and we need to change the type of sensors, or we need to choose another outlets.
Thank you. This is interesting. I mean, we are using sensor for so many things now, and there are so many pros and cons, so it's good to know both. The next question is for Chris again, and the question is from Beniamino Russo, and he's asking, which is the area interested by SADS implementation respect to the total area of the catchment, and could diffuse use of SADS achieve better results in terms of a hazard reduction in this case?
So, sorry, so the first bit, which is the best?
Which is the area interested by SADS implementation with respect to the total area of the catchment?
Oh, I see. So how much land do we need?
Yeah.
I guess that depends on what type of SUDS we're implementing. The typical, we're finding for a site of typical value was taking up around 10 to 15% of the site. That's using a combination of swales, basins, and other smaller things such as green roofs, which does impact on development. It does mean that buildings will have to be reduced, and we wanted that to be understood. What was the second question again, sorry?
Could diffuse use of SADS achieve better results in terms of hazard reduction?
Yeah, I think actually our our project moved more towards flood resilience approach. The issues of land being raised, displacing flooding, it's no secret that the land, sorry, excuse my voice, would need to be raised, but there was no consideration for where this floodwater goes. The solution to that isn't just SUDS, it needs other infrastructure as well. And we do see it as part of the solution, not the solution.
Yeah, no, I agree that the solution would be a sort of a portfolio of options, right? Rather than just one that to fit all, again, as was said before. Thank you, Chris. Next question is for Alejandro. And the question is about the estimation of benefits from damage reduction. So which method did you use? For example, how did you compute the reduction to the risk mobility?
Okay, it's not easy because there is a complex methodology. That this methodology combine cost evaluation, damage curves, experimental damage curves, with a hydraulic model in 2D. The hydraulic model is in 2D combining traditional model, and this model is made in the casa and in take account all the network, 1,600 kilometers of network. And this is a combination in the hydraulic model with the experimental damage curves.
Fantastic. No, this is very interesting. And I'm actually wondering if you have published anything about your method, or if you have reports that you can share with a larger audience.
If I can report the results of the methodology, yes, I can. But no, now no.
Yeah, okay, no, thank you. I will,
If
perhaps
anyone is interested, I can report, because the results is in the master plan. The master plan is official. Then you can visit the link in the BCN rock. Is a public repository when you can see the master. In this master plan, there are all the figures, results, and justification.
Thank you. Thank you so much. No, it's great. I have two last questions, and the first one is for Elena. The question is about the index of retention. Which kind of potential further application do you see for this index? How can be applied further? For example, thinking about flooding simulation and design for a flooding reduction.
Well, it's for sure a good measure of how much water is retained. So of course it can be applied at the single building scale or at the city scale. So when you apply it at the city scale, of course you get an idea of how is the reduction of the peak, so of the runoff generation. So it's it's a powerful index in order to estimate the peak reduction for sure, and the total generation runoff reduction. So both in terms of peak and in terms of the total volume. So it's for sure something that can be applied to have a good estimation of the risk reduction to some extent.
Yeah, I think this would be very valuable, for example, for simulation exactly of risk reduction and plans at larger scale. So no, thank you for your answer. It's great. The last question is for Alejandro again, and it's from Eduardo Martinez Gomaris. He's saying that your plan is definitely different from the traditional approach of master plans. And he's wondering if you think that this kind of approach, of risk-based approach, can be applied to other cities, or do you see any peculiarities linked to Barcelona that make your plan unique?
Well, it depends. I'm agree with Eduardo Martinez. I recommend that this is a new methodology. It can extend it to every cities, but it depends of the administration.
And resources, I guess. Did you think that your plan was most expensive than others, or?
No, it's not expensive, because the result indicates that it's an efficiency plan. But to reacting to the master plan is complicated, and it needs a team, a specialty team of engineering, and it's not easy.
Thank you. Thank you, Alejandro, for this last answer. And also thank you. I really thank you personally, all the presenters for this morning, especially for this early start of the parallel session. And I thank you also the audience. Thank you for all the questions. I know the setting, this particular setting was a bit different compared to normal conferences, but I think our sessions were very well. And so I thank you all again, and I wish you a nice continuation of the day. This session is closed, and I invite you to take a break now and to follow other parallel session of the conference. Thank you very much.
Okay,
Thank you.
Thank you.
Thank you, everybody.
Thank you. Bye-bye.
Bye.